Hi everyone, welcome to part 1 on our video lecture for section 3.5 dealing with the derivative of trigonometric functions. In this set of videos, we're going to be taking a look at the proof for the derivative for the sine function and then use the derivatives for the other trig functions on a couple of examples. Alright, so now that we know how to find the derivatives of products and quotients, let's see if we can find the derivatives for trigonometric functions. Alright, so in order to motivate the topic and give you a sense of what to come, I want to begin by taking a look at the graph of the sine function. So let's sketch the sine function. The sine of 0 is 0, the sine of pi over 2 is 1, the sine of pi is 0, sine of 3 pi over 2 is negative 1, and the sine of 2 pi is 0. And this gives us our sine function on the interval from 0 to 2 pi. Alright, perfect. Now, how would the graph of the derivative look like? Alright, so let's take a look here. And again, I'm going to go ahead and keep on following the same techniques that I discussed in class. So I'm first going to identify where do the tangent lines seem to be horizontal. Alright, so I see some horizontal tangent lines right over here at pi over 2. So that means that the derivative is 0 at pi over 2. And I also see a horizontal tangent line at 3 pi over 2, which means that the derivative is 0 at pi over 2. Okay, now where's the sine function increasing? In other words, where is the derivative positive? Well, I get to see here, and again, using the techniques that we discussed in class here, picturing some slopes, I do get to see here, okay, my tangent lines are positive here, and yeah, you get to see here that closer to 0, the tangent lines were a little bit steeper, but as you approach the pi over 2, the tangent lines became shallower. Now, I'm going to go ahead and say that the slope right over here was 1. So I'm going to go ahead and start at 1 here, and then as our tangent lines became shallower, that meant our derivative values became shallower and approach 0. Let me make this nicer here. Something like this here. Okay, now taking a look at the intervals of decrease for the sine function, you get to see here, okay, some steeper tangent lines, steepest here at pi, but then started to become shallower again here as you approach the 3 pi over 2. Alright, so somewhat shallow here after the pi over 2, became steeper, then they started to become shallower again to reach 0 at the 3 pi over 2. Now, let's go back to the increasing intervals. So again, we start off with positive slopes, shallow, become steeper, steeper, and steeper here. Alright, so that means that we're going back to positive values for the slope. And it should look something like this. Alright, now, taking a look at this sketch for the derivative, hopefully it looks a little bit familiar. This looks a lot like the cosine function. Now, is that true though? Well, now let's actually go ahead and prove what is the actual derivative for the sine. Maybe it is a cosine function. Now, before we take a look at the proof though, I will ask you guys to consider the following limits. Now, I'm not going to go ahead and prove these ones here. I'll just reference them. But the limit as h approaches 0 for the sine of h over h is equals to 1, and the limit as h approaches 0 for the cosine of h minus 1 over h is equals to 0. Okay, now that we have these limits at our disposal, let's go ahead and take the derivative for the sine function. Alright, so using the limit definition of the derivative, we'll have here f prime of x is equals to the limit as h approaches 0 for the sine of x plus h minus sine of x, and it is all over h. Now, notice here that we are encountering the sign of a sum. Well, there's a trig identity that we can use. The sign of a sum, specifically here the sign of alpha plus beta, is equals to the sign of alpha times cosine beta plus the cosine of alpha times sine of beta. Now, in the context of our problem then, sine of x plus h is going to be equals to sine of x times the cosine of h plus the cosine of x times the sine of h. Alright, so I'm going to go ahead and substitute this into our difference quotient, or our limit definition for the derivative. Alright, so let's take a look here at the next page, where I worked a little bit ahead to get the derivation for the derivative of the sine function. Alright, so let's go ahead and begin here with the limit definition for the derivative. So we have here the limit as h approaches 0 for the sine of x plus h minus sine of x all over h. Perfect. Now on the next line, I went ahead and used our identity for the sign of a sum. And that's how we got the limit as h approaches 0 for the sine of x times the cosine of h plus the cosine of x plus the sine of h minus sine of x all over h. Now, for the next line here, I decided to group the signs closer together. So notice here that we have a sine of x here and a sine of x here. So I place them closer together to get the limit as h approaches 0 for the sine of x times the cosine of h minus the sine of x plus the cosine of x times the sine of h, and it's all over h. Now, since I grouped the sine of x's closer together, notice that we can go ahead and factor a sine of x from these two terms, which gives us the limit as h approaches 0 for the sine of x times, parentheses, cosine of h minus 1 plus the cosine of x times the sine of h all over h. Now, because I'm dividing everything by h here, and I have a couple of products on my numerator, I'm actually only going to go ahead and divide the cosine of h minus 1 by h, and I'm going to go ahead and divide the sine of h all over h as well. Now, what is that going to give us? Well, this now gives us the limit as h approaches 0 for the sine of x times the cosine of h minus 1 all over h plus the cosine of x times the sine of h all over h here. Now, what can we do here? Well, notice that we're taking the limit as the h approaches 0, but I do have a sine of x and a cosine of x that don't have any h's, so they're not really affected by the limit. And in fact, let me go ahead and include this in between step here. Here we go. Let me just move this a little bit around here. Perfect. Okay, now, since the limit is only for the h's, on the first term here, you get to see here that we have the limit as h approaches 0 for the cosine of h minus 1, but taking a look at the previous page here, the limit as h approaches 0 for the cosine of h minus 1 all over h is equals to 0 here. Okay, so this is just 0. Now we also have the limit as h approaches 0 for the sine of h over h. Now, what was that limit? Again, taking a look at the previous page, you would have seen that this limit is equals to 1. Now that we've valued the limits, what are we left over with? Well, actually, this limit is already used. There we go. So we then have the sine of x times 0 plus the cosine of x times 1. Well, if we're multiplying the sine of x times 0, well, that's gone. And we're just left with a cosine of x. So it turns out that indeed, if you started off with f of x as the sine function, then f prime of x is equals to the cosine function. So our sketch in the previous page was actually very close. Now, what about the derivative for the cosine function? Well, a similar proof using the cosine of a sum, given here by the cosine of alpha times cosine beta minus sine of alpha times sine beta, can be used to show that if your starting function was a cosine, then the derivative function, f prime of x, will be the negative sine of x. Now, these are going to be two formulas that I want you to remember. The derivative for a sine is cosine, and the derivative for a cosine is a negative sine. But what about the rest of the trigonometric functions? Well, lucky for us, we can use a technique that we've already discussed. We can use the quotient rule. So let's go ahead and use the quotient rule to find the derivative for the tangent function. So let's see, what is the derivative with respect to x of the tangent of x? So since I mentioned here that we can use the quotient rule, well, where does the quotient rule come into play? Because I just see a tangent function. I don't see no quotient, no fraction. Well, we can go ahead and rewrite the tangent function as the sine of x over the cosine of x. So we do have a quotient, so we can go ahead and use the quotient rule now. Just a quick refresher, I've included the quotient rule here. If you're taking the derivative quotient, f over g, then the derivative is going to be g times f prime minus g prime times f, and it's all over g squared. Now remember, for this first couple of examples, I actually want you guys to break the derivatives down by first identifying, okay, what is the f function, the numerator, and what is your g function, the denominator. Well, for this problem, our numerator is the sine of x, so what would be f prime here? Well, as we just saw, the derivative of the sine is a cosine of x. Now, our denominator here is the cosine of x. So what is g prime? The derivative of the cosine. And as we just saw, this one here is a negative sine of x. So now that we've identified the f, the g, and their respective derivatives, let's actually go ahead and put all the pieces together using the quotient rule here. So the derivative of sine of x over cosine of x is going to be equals to cosine of x times the cosine of x minus a negative sine of x times sine of x all over cosine squared, which again is just our g times f prime minus g prime times f over g squared. All right, now let's simplify this one here a little bit further. Since my first term on the numerator is a cosine times a cosine, I'll rewrite it here as a cosine squared of x. Then I have a negative times a negative sine of x, which is going to give us a positive. But since you're multiplying two signs, we're going to get a sine squared of x all over a cosine squared. Now, can we simplify this? Well, notice that on the numerator we have a cosine squared of x plus a sine squared of x. Now, hopefully this formula looks a little bit familiar because this is the Pythagorean identity. We know that when we have cosine squared of x plus the sine squared of x, we will always be getting a 1. Well, then what does this tell us? Well, this tells us then that the derivative for the tangent function is equals to 1 over a cosine squared of x. The thing is, I also recognize the 1 over cosine squared as another trig function. Remember, the 1 over cosine is exactly the same thing here as the secant function. So 1 over cosine squared then is the secant squared of x. And there we go. We've come up with a nice form of the derivative for the tangent function. The derivative for the tangent of x is simply the tangent cosine of x times the cosine of x minus a negative sine of x times sine of x all over cosine squared, which again is just our g times f prime minus g prime times f over g squared. All right, now let's simplify this one here a little bit further. Since my first term on the numerator is a cosine times a cosine, I'll rewrite it here as a cosine squared of x. Then I have a negative times a negative sine of x, which is going to give us a positive. But since you're multiplying two signs, we're going to get a sine squared of x all over a cosine squared. Now, can we simplify this? Well, notice that on the numerator we have a cosine squared of x plus a sine squared of x. Now, hopefully this formula looks a little bit familiar because this is the Pythagorean identity. We know that when we have cosine squared of x plus the sine squared of x, we will always be getting a 1. Well, then what does this tell us? Well, this tells us then that the derivative for the tangent function is equals to 1 over a cosine squared of x. The thing is, I also recognize the 1 over cosine squared as another trig function. Remember, the 1 over cosine is exactly the same thing here as the secant function. So 1 over cosine squared then is the secant squared of x. And there we go. We've come up with a nice form of the derivative for the tangent function. The derivative for the tangent of x is simply the secant squared of x. And there we go. Now, if you wanted to find the derivative for the cotangent, the cosecant, the secant, for example, then yeah, we would be following similar procedures. However, now I actually want to give you the formulas for the derivatives of the trig functions. And here we have them. And these formulas you will need to memorize, guys. All right, so let's see, what are they? Well, as we discussed, the derivative with respect to x for the sine function is the cosine of x. The derivative of the cosine of x is a negative sine of x. The derivative for the tangent is the secant squared of x. Now, the ones we haven't seen, the derivative for the cosecant is a negative cosecant cotangent. The derivative for the secant is a secant tangent. And the derivative for the cotangent is the negative cosecant squared. Now, I want you guys to notice something, and hopefully this helps you remember them. If your trig function begins with a c, then it's going to have a negative derivative. So notice this. The derivative for the cosine is a negative sine. The derivative for the cosecant is a negative cosecant cotangent. And the derivative for a cotangent is a negative cosecant squared. Okay, now we're going to practice finding some derivatives involving trig functions, and I want you guys to reference these formulas here. You will use them, and you'll keep on using them for the rest of the class, so might as well start to get comfortable with them. All right, so let's begin here with this example where we're trying to find the derivative of the following function. F of x is equals to the secant of x all over 1 plus the tangent of x. Okay, so for this problem here, it seems like we're having another quotient, so we will need to use the quotient rule. Okay, so for this particular function, which one is going to be our f? Now again, remember the f is not the original function. I'm just using f to represent the numerator and g to represent the denominator. So in this case, the f is the secant function, and the g is the 1 plus tangent of x function. All right, so let's go ahead and figure out the derivatives. So what is going to be the derivative for the secant of x? Well, if you scroll up, what was the derivative of the secant? Oh, it's the secant times the tangent. So f prime then is going to be the secant of x times the tangent of x. Perfect. Now what about the derivative for 1 plus the tangent of x? In other words, what will be g prime here? Well, the derivative for 1, a constant, is 0, plus the derivative of the tangent, which we just discussed here, was the secant squared of x. Perfect. I got the f prime, and g prime. So now we can go ahead and place them into the format for the quotient rule. So what are we going to get? Well, let's take a look here. So the derivative for the original function is going to be 1 plus the tangent of x times the secant of x times the tangent of x minus secant squared of x times secant of x, and it's all over parentheses 1 plus tangent of x, whole thing squared. Okay. Now, because I said that on exams I don't want you to simplify, this would be a good enough answer. But on the homework, some problems you may need to simplify. So I'm going to go ahead and simplify this one. All right, so what can we do here? Well, for starters, I know that the numerator, I have a secant of x on the first term and a secant of x on the other term. So I'm going to go ahead and factor out a secant of x. So we're going to get then that the derivative is equals to the secant of x times all of this, the 1 plus tangent of x times tangent of x, minus a secant squared of x, and the whole thing is being divided by parentheses 1 plus tangent of x squared. Now, I'm going to go ahead and distribute this tangent of x to see what we get. All right, so this is going to give us a secant of x times tangent of x plus tangent squared of x minus secant squared of x, and it's all over the parentheses 1 plus tangent of x squared. All right, now why did I choose to distribute the tangent? Well, it's because I wanted to see if I can get maybe a tangent squared and a secant squared, which we actually do here. We have tangent squared of x minus the secant squared of x. Now, can we rewrite this one here using an identity? And this is where the Pythagorean identity, again, can come into play. So we discussed the Pythagorean identity in the previous problem, or with the derivation for the derivative of the tangent. And we said here that if we have the sine squared plus cosine squared of any angle, that's just equals to 1. But right now we don't have any sines or cosines. Instead, we have tangents and secants. Well, I'm going to go ahead and take my Pythagorean identity and see if I can get a tangent and a secant there. And we can obtain this tangent and secant by dividing by cosine squared. Now you see, once you divide by the cosine squared, we're going to get cosine squared divided by cosine squared. That's just going to be a 1 plus sine squared over cosine squared. That is going to be a tangent squared is equals to a secant squared, because 1 over cosine squared is just the secant squared. Now for this problem, we have a tangent squared minus secant squared. So what I'm going to do here is rewrite our identity once more. I'm going to go ahead and subtract the secant squared from both sides, as well as subtracting a 1 from both sides. All right, so what are we left with? Well, you get to see here that we're left with a tangent squared of x minus a secant squared of x is equals to a negative 1. So now I know that all of this, the tangent squared minus secant squared, is the same thing as a negative 1. Okay, now we're going to get a much simpler form for the derivative for this function. We're going to be left with a secant of x times the tangent of x minus 1 all over parentheses 1 plus tangent of x squared. Okay, now, do you need to simplify all the problems like this? No. Again, remember, on the exams, I'm not going to ask you to simplify, unless it's an easy simplification. But on the homework, you may need to. And this is where, again, the trig identities, namely the Pythagorean identity, really shines. Okay, so I figured this is going to be a good place to stop our first part of the recordings, and we'll continue on with more examples in part 2. See you there.